Years ago, President Obama asserted that we must harness the power of nuclear energy to combat climate change and to advance peace and opportunity for all people. The President has made it clear that his administration and the United States must remain committed to nuclear energy as part of a diversified, low-carbon energy portfolio whose goal is to reduce global air pollution and promote energy security. This past January, during the President's State of the Union address, he outlined the vision for powering the future. Part of that vision was the need for innovation, and in particular innovation in clean energy technologies. He set a very ambitious goal of obtaining 80% of our electricity from clean energy sources by 2035. Since nuclear power currently accounts for about 70% of the carbon-free electricity, this goal can only be achieved with the addition of safe nuclear energy to our future energy portfolio. Now, I would be remiss if I did not acknowledge the accident at Fukushima and its potential impact on the commercial industry, both here and abroad. It represents the most serious nuclear crisis the world has seen in nearly a quarter century. Japanese efforts are ongoing to contain the accident and mitigate further environmental effects. In the U.S., DOE has launched a review of its nuclear facilities, and the NRC is reviewing the current operating plants. There's no doubt in my mind that the nuclear energy community will be studying the accident at Fukushima for some time to learn from that accident and determine the best course of action for existing and future nuclear power plants. It will be our challenge, DOE, NRC, and the U.S. nuclear industry, to take the lessons learned from Fukushima and strengthen safety and security at our existing plants, as well as incorporating these lessons into future advanced reactor designs. The continued safe operation of the U.S. nuclear fleet is of paramount importance, and we at the Department of Energy are committed to continuous safety improvements at all our nuclear facilities. Before continuing, I'd like to point out that the Department's guiding principle for its R&D program over the last 3 decades has been to support advanced technologies that offer improvements over Gen 2 reactor designs in terms of safety, security, and economics. This strategy will continue in the future. So this morning I'd like to review some of our R&D programs that address current and future reactor systems. These programs are aimed directly at improving safety, security, economics, the sustainability of nuclear power, as well as building the nuclear infrastructure to sustain the nuclear renaissance in the future. And I'll conclude with some thoughts on the future of nuclear power in the United States. The accident at Fukushima, even though not fully understood yet, clearly challenged the operators in many complex ways. The complete station blackout and loss of ultimate heat sinks were extremely difficult to handle. One approach to dealing with such challenging scenarios is to emphasize passive safety features that rely on natural forces such as gravity and require less operator intervention. In general, passive safety designs require fewer operator actions, rely extensively on natural phenomena such as large quantities of stored water, gravity feed instead of pumps, and convective cooling in accident conditions. They do not require operator actions for long periods at times and do not depend on off-site or emergency diesel generator power to maintain safety. Nuclear plants with passive safety features offer the greatest promise for still safer operations in the future. With such an emphasis in mind, the U.S. government undertook a cost-shared effort with industry to advance 2 passive reactor designs towards realization. This was the NP 2010 program. There are many important outcomes of this program, not the least of which is that the U.S. Nuclear Regulatory Commission is now in the final stages of evaluations of design certifications for both the Westinghouse AP1000 and the General Electric ESBWR. The AP1000 is a 2-loop pressurized water reactor with passive safety systems and extensive plant simplification that improve plant operation and maintenance while reducing construction cost and schedule. The AP1000 plant safety systems use only natural forces such as gravity, natural circulation, and compressed gas to provide the driving forces for the systems that cool the reactor core following an accident. These critical safety systems do not rely on pumps, fans, chillers, or diesel generators for accident response, nor is there any reliance on safety-grade power. Some of the AP1000's passive safety features include core makeup system, pressurized accumulator, passive residual heat removal, automatic depressurization, and passive containment cooling. Safety systems have been simplified to minimize the number of active components that need to be actuated following an accident. For example, there are very few motor-operated valves, and in most cases these valves fail safe. By using in-containment storage of water, the need for pumping of water after an accident is eliminated. Containment heat removal is accomplished through the use of passive water and air cooling systems. The AP1000 is designed to maintain safe shutdown for 72 hours after a design-based event, and that's without any external power. With external power, much longer times can be obtained. In our view, using passive technology features prevents and mitigates the effects of accidents and offers the best path forward in terms of safety, and the AP1000 has many advanced passive safety features. Currently, AP1000 is being used in 6 active projects in the U.S., and worldwide there are 8 AP1000s units ordered, 4 are under construction in China, and 4 in the U.S. are proceeding under a limited work authorization. And China has also indicated the potential for ordering additional AP1000 units. Our view, the realities of these orders is directly correlated to the success of the NP 2010 program. The Economic Simplified Boiling Water Reactor, or ESBWR, is a 1594 megawatt electric version of the advanced boiling water reactor that used economy of scales, proven technology, and components from that reactor to create a new reactor at reduced capital cost. The ESBWR plant relies on the use of natural circulation and passive safety features to enhance the plant performance and simplify the design. The use of natural circulation allows the elimination of several systems and components, such as emergency core cooling, pumps, and the recirculation system and its support systems. ESBWR utilizes the isolation condenser system for high-pressure inventory control and decay heat removal. After initialization of the automatic depressurization system, low-pressure inventory control is provided by gravity-driven systems. Containment cooling is provided by the passive containment cooling system, which is the only new major system. It is designed to provide core cooling for 72 hours without external AC power or operator action, and the risk of core damage from station blackout is a factor of 1,000 less than conventional boiling water reactors. In the ESBWR, the core will remain covered for the entire range of design-based accidents. And as I mentioned previously, the design certification for the ESBWR is expected to be issued this year. I'd now like to turn to small modular reactors, or SMRs. These are an area of great interest to DOE, and we see SMRs as game-changing technology, offering notable safety, security, and economic advantages. For example, the Light Water SMR designs incorporate passive safety features that utilize gravity-driven systems rather than engineered pump-driven systems to supply backup cooling in unusual circumstances. Some concepts use natural circulation for normal operations, requiring no pumping system and providing a still more robust safety case. In addition, many SMRs utilize integral designs for which all major primary components are located in a single pressure vessel. That feature results in a lower susceptibility to certain potential events, such as the loss of cooling accident, because there is no large external primary pump piping. Lastly, because of their lower power level, SMRs have a lower level of decay heat and therefore require less cooling after reactor shutdown. SMRs have been designed to address both the safety and security while lowering the capital cost barrier for market penetration. The SMR concepts of immediate interest are based upon the well-understood light water reactor technology. This is important because the regulatory base and experience are built on this technology. The choice to stay within the proven performance envelope of the existing commercial low-enriched uranium nuclear fuel cycle has 2 important benefits. First, it means that the most promising near-term SMRs can build upon the well-established light water reactor fuel industry, avoiding the need to establish a parallel fuel manufacturing capability. Second, this fuel cycle minimizes the technical risk of the most demanding technology component of any new reactor system, namely the new fuel design, and improves the time to license within the current NRC regulatory system. The Department is working with the House and Senate Appropriations Committees, as required under the FY11 Continuing Resolution, to determine a path forward for the program for the remainder of this fiscal year. This program is designed to assist industry in their efforts to receive design certification for reactors designs and to obtain construction and operating license for the nuclear plants with a targeted first deployment within a decade. Now,